Today we'll be discussing containerization in cloud systems design. Subscribe to the channel and like this video for more great cloud tips. Containerization is an important part of cloud compute in systems design, alongside virtual machines and serverless functions. A container packages your application with its libraries, runtime, and configuration into one unit. That unit is built from a container image. It is a read-only template that runs identically anywhere. Portability is the whole point. You build once, then run on a laptop, a pipeline, and across multiple different cloud providers. A container image is the artifact you build once, and a container is a running instance of it. Containers share the host kernel instead of booting their own, so they start in under a second. You get immutable infrastructure almost for free. Why is that free? Because you replace a container rather than patching it. Cloud-native architecture assumes exactly that, and every managed platform now speaks the same packaging format. Environment drift between a laptop and production mostly disappears. Containers are not virtual machines, and the isolation comes entirely from kernel features. Namespace isolation gives each container its own view of process IDs, network interfaces, and mounts. cgroups, short for control groups, enforce resource isolation. They cap CPU, memory, and I/O. A container runtime, such as Containerd or CRI-O, wires those pieces together. Docker popularized this. It handed the image format to the Open Container Initiative, or OCI. A Docker image is not one blob, it is a stack of layers. Each build instruction adds a layer, and a layered file system like Union FS merges them into one directory tree. What does that buy you? Image layers are content addressed and shared, so 10 services built on one base image download that base once. Only changed layers get rebuilt and pushed, which is why a code-only change ships in seconds. Order your build steps from least to most volatile. Dependencies first, application code last. Multi-stage builds compile in one stage and copy just the finished binary into a second tiny stage. Your compiler, package manager, and build caches never reach production. A full operating system image can exceed a gigabyte. Alpine lands near 5 megabytes. Distroless images ship only your runtime. Smaller images pull faster and carry far fewer vulnerabilities. An absent package cannot be exploited. Pin your base image by digest rather than by a floating tag. A container registry is where your images are pushed to and pulled from. Docker Hub is the public default, while ECR on AWS, ACR on Azure, and Artifact Registry on Google Cloud give you private access-controlled storage. Enable image signing so only images your own pipeline built can run. Why keep a copy close by? Keep a replica in every region you deploy to, because a cross-region pull is slow exactly when you are scaling out. A few hundred containers across a fleet need container orchestration. Kubernetes is the standard, sold as a managed service through AWS EKS, Azure AKS, and Google GKE. Its smallest deployable unit is the pod. That is one or more containers sharing a network namespace and volumes. Containers as a service offerings like ECS, Cloud Run, and Azure Container Apps hide the control plane entirely. Start there and take on Kubernetes when you actually need its extensibility. Liveness probes ask whether the process is still functioning, and a failure triggers a restart. Readiness probes ask whether it can serve traffic. A failure removes the pod from the load balancer. Rolling updates replace old pods a few at a time, so a bad release stalls instead of failing the service. The horizontal pod autoscaler then adds replicas against CPU or custom metrics like requests per second. The Sidecar pattern runs a helper container beside your application in the same pod. A service mesh like Istio or Linkerd scales that across the cluster. It injects a proxy into every pod for mutual TLS and traffic splitting. State is harder because containers are ephemeral. They lose their local file system on restart. Persistent volumes attach durable storage that outlives the container. Stateful sets give each replica a stable identity and its own volume. Get more cloud tips at systemsarchitect.io. Like and subscribe to the channel. Follow the playlist. Operations improve most because one deployment mechanism now covers every language your teams write in. Portability follows. The same image runs on a laptop, in a pipeline, and across 3 providers. Cost drops through density. Dozens of containers pack onto a node that once hosted a few virtual machines. Reliability improves because restarts, rescheduling, and rolling updates belong to the platform rather than a runbook. Security tightens when a minimal image and a non-root user shrink the attack surface. Containers add a build pipeline, a registry, and an orchestrator to run. For a small application with steady traffic, a managed platform service or a plain virtual machine is less to operate. For spiky, event-driven work, serverless functions scale to 0 and bill per invocation. Kernel isolation is weaker than a hypervisor's, so hostile multi-tenant workloads want micro VMs or separate nodes. Heavy stateful systems with strict I/O demands often run better on a managed database service. Containerization packages an application and its dependencies into a portable image, isolated by kernel namespaces and cgroups rather than by a hypervisor. Layered images, multi-stage builds, and a registry make distribution fast. Orchestration adds scheduling, health probes, autoscaling, and rolling updates. Keep images minimal, push state out to persistent volumes or managed services, and adopt only as much orchestration as your workload needs. Thanks for watching and listening to this, and subscribe to the channel. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io.